Hi, this is Peter with CalcBook, and today we're going to be looking at point loads on flanges. So we're going to be looking at two different analysis methods. The first is called yield line theory, and then after this, we'll take a look at just a simple cantilever method. But first, about yield line theory, right? It's a method that was developed for designing reinforced concrete slabs or similar type of plate elements, and it relies on the development of plastic hinges in these certain sort of patterns to determine the capacity. And one thing along that, right, is it does require a really sufficient understanding of failure patterns and how they develop. So it's sort of an advanced topic with engineers with experience, but we wanted to give our users the opportunity to use this. And a couple kind of just warnings or disclaimers about using this method is that one, it really gives an upper bound solution. So in the case of the point load on a flange, it would give you the kind of a really thin or the thinnest possible flange required to support that loading. And the other thing is that the deformation of the plate is not considered. So you could get a really thin plate, but you may not actually develop those deformations, to get that capacity. So it's just something to keep in mind. There's a lot of really good information about this in a document called the Practical Yield Line Design, and we'll provide a link to that in the comments below for you to take a look. So just kind of quickly in that diagram there, right? That's where the point load is. That orange dot in that plan view. We're looking at the bottom flange there. We've got our yield lines that develop, right? So this is sort of an understanding of how we think that this bottom flange is going to deform under that load. And then we've got our boundary conditions that we're assuming on the three sides of that flange there. So the second method is just a simple cantilever method, right? I think most of us are probably pretty familiar with how this works, right? We're going to assume a 45-degree failure plane from the point of the load back towards the flange, right? This assumes a full cantilever action from the face of the web to the location of the point load, which means that it's not going to rely on any of the support that you would get from the continuous flange on either side of that point load. So again, right, we've got our point load here, that orange dot, right? We got our failure path of 45 degrees back to the flange, or excuse me, back to the web. And then this is going to be our effective bending section when we take a look at it in cantilever action. Okay, so before we look at the problem statement, just sort of a couple real life examples, right? So where you would get, point loading on a flange, right? Maybe a beam clamp of some sort, right? A couple different types of beam clamps here, or maybe a crane rail, right? And then I'm sure we're all pretty familiar with unistrut attachments and applying those to the bottom of a flange. So just a couple examples of what this actually might look like. So our problem statement for today, we're going to assume that we have a W12 by 40. So that's going to be a couple different parameters there for what we're going to need for the calculation. We're going to assume a unistrut is attached to the bottom of the beam flange, right, at that location P. We're going to assume the load is applied at the edge of the flange. So for the cantilever method, right, that A value is just going to be all the way to the edge. For the yield line theory, same thing. A will be all the way to the edge, and that B value in the lower right will be 0. And we're going to assume we have an applied dead load of 3,500 pounds that we're trying to support. So we're going to check the flange capacity with both analysis methods. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, we've got CalcBook open now, and we can go ahead and click into our steel design. You can see now that we've got two options. We have the 16th edition or the 15th edition of AISC. For this particular calculation, it doesn't really matter, but we'll go ahead and use the latest and click into the 16th. Click into our connection design, and then we'll scroll down here and click on our point load on flange design module. So we've got two options here to choose from, right? Like we talked about, our yield line theory or the simple cantilever method. And we have this info button here, which summarizes sort of what we talked about earlier. You guys can read this in more detail. But we're going to check both. So to start, though, we're going to do a cantilever method. So first thing we need to do is enter in our distance from the web face, right, this A dimension. We decided that it's going to be all the way out at the edge of the flange. So I already did this calculation, right? It's going to be 3.8575, and that's just half the distance, or half the web distance, flange distance minus half of the web. Gets us that cantilevered distance for the loading. And then we need to enter in our length of bearing, right? And what this is, if we look at the beam sort of, in elevation, the beam running this way, we want to know sort of what that contact length is, what that bearing length is, to determine, our basically what's going to be our bending section. So for this, it's going to be basically the width of the unistrut clamp, and that is 3 inches. So the unistrut's 1 5/8 inches, and then the clamp and it bearing on the beam flange is 3 inches. And then the thickness of our loaded flange, right? We're using a W12 by 40, and that's going to be 0.515, and we're going to assume FY50, so A992 steel. And then we want to enter in our demand, right? We have a applied dead load of 3,500, so 3.5 kips. Okay. And then we can go ahead and check into our calculation here and see how this all comes together. So, right, we've got our concentrated load, and we're just going to be using the LRFD load combination 1, so 1.4 times dead gives us a load of 4.9 kips. And then we want to determine the moment on the flange, right? It's pretty straightforward. Just our loading, our point load P times the distance A. So 4.9 kips times 3.86 inches gives us a moment of 18.9 kip inch. And then we calculate the capacity, right? So just based on kind of a regular rectangular bending section, right? First thing we need to do is determine what our actual length of bending is, right? Our length of our bending section, our capacity section. So it's just going to be our bearing length, and then 45 degrees back to determine that L prime value, which gives us a length of 8.46 inches. From there, we determine our elastic section modulus and our plastic section modulus. And then finally, we just determine what our bending capacity is based on the yielding strength for basically what is a rectangular bar. So we get a capacity of 25.23 kip inch, right? And based on our demand of 18.9, we have a DC ratio of 0.75. So our design is okay. So now let's go back and do the same thing for yield line theory, right? So the only thing we're going to change, we're just going to toggle this over to yield line theory. And we need to enter in this B distance, right? And again, since we decided that our load is all the way out at the edge, that B distance is going to be 0. So we'll just enter in 0 for that, right? Our thickness stays the same. Our loading stays the same. And now we can go take a look at how the yield line calculation is performed. So we need to figure out this distance X, right? Which is the distance from our point load to our boundary condition, along the length of the beam. So where we're going to pick up that boundary condition due to the continuous flange, basically. There is quite a derivation here. You guys can look that up, and it's also talks more about it in that document that we posted in the comments below. We're not going to go through all this, but you guys can take a look at that, and you can provide some comments if you guys have any questions for us. So based on this, on the boundary conditions and these dimensions, right, we can get a nominal plastic strength of the flange using the yield line theory, which gives us a capacity of 18.75 kips. And then our design capacity, if we add our feed factor to that, is 16.88 kips. And since our demand is only 4.9 kips, you can see we have a DC ratio of 0.29. So it's about a third of what we get with the cantilever method. So just keep that in mind when you guys are doing this design, that these two are kind of the upper and lower bounds of the design. And just make sure that you really understand the yield line theory before you proceed using that method. So that's point loads on flanges in CalcBook. We hope you enjoyed this video, and we'll see you next time.